All right, everyone. So let's start today's seminar. Today's seminar is by Jason Hearst. He's a professor at Norway University of Science and Technology, and he's currently on sabbatical in Toronto. So he paid us a visit. Jason did his PhD at the University of Toronto. And then he worked as a postdoc at the University of Southampton in the UK. And his research background is in experimental fluid mechanics and turbulence. So, Jason.
Thank you, Martin. So I realize I'm competing with like other lectures at this university and with the school break. So thank you for coming. Could take this maybe a tad more informally. So if you have questions, feel free to ask in the middle instead of waiting. Hopefully there's some entertaining things in here. Our broad program is largely based on how turbulence affects other problems. So these things may not seem related to each other, but the way they're related to each other is actually in this part, how turbulence affects them. So I'll show you how we actually do these experiments, which is also the part of like science that I like doing, is doing cool experiments. As you may already know, or you will find out, like basically anything Professor ever shows you is really the work of a big team of people. So these are the people that contributed to the talk today. They're not in any particular order, but lots of people contributed to the results I'm going to show you. This is the group right now. Just broadly, the only thing I'm going to say is for those of you who want to go to Europe, this is a new conference that's made to be kind of APS style. So this is something that I think it's good to grow for anyone who's crossing the ocean. The next one's in Dublin, but then the one after that's in 2 years. Or you can target this maybe. So just a little bit of like geographic context. So I'm in Toronto right now on sabbatical, and I'm visiting you guys over here in Michigan, but where the university I'm from is actually up here in Norway. Usually when I show this plot, I'm giving talks in Europe, so like I just do this. There's a big ocean in the middle right now, though. Then the next question we get when we talk about this is where are we relative to the Arctic Circle, and where below the Arctic Circle. So we don't get 24 hours of light and darkness. We do get the Northern Lights, though. Every university has a Harry Potter building. I assume you have one. I haven't seen it yet. So this is the Northern Lights over our Harry Potter building. And we have all the seasons just like you have here in Michigan. So it's not like we're just living with the polar bears. It's, you know, a regular place with all the seasons. The university has 40,000 students, so it's a little bit smaller than here, but it's a giant university. And these are just some pictures of the city and the local fjords. And this is literally my house with the Northern Lights over it. So it's an idyllic place. I have worked broadly in 3 areas. One is fundamental turbulence, which was parts of my PhD. Another one is also fundamental turbulence. Another way, it's boundary layers. So particularly what those are showing you is how free stream turbulence affects the flow on a wall. So how a boundary layer is influenced by putting turbulence above the boundary layer. And the other one is what I'm going to show you today, which is how ambient turbulence affects other problems. And the broad way we do that is by using these devices, which are called active grids. I'm going to talk a little bit more about these, but what you're looking at is basically we're controlling the way these flaps are moving. For context, this is how big our biggest one is. So this is Hilda. Hilda's the same size as I am. So this is our wind tunnel, and you can see the device is a human size. You don't put your hand in there because it'll hurt. What this is the active grid device is placed at the front of the wind tunnel, inside the test section. So the air goes from the screen through that device towards you. And you can imagine that as air tries to get through this, that it must become very turbulent as it moves downstream. The advantage of using this device is we can basically change the way these wings move to create different patterns in the flow. We have these devices in both our water channel and our wind tunnel. These are relatively big facilities. They're both about, so the water channel is 2 meters across by 1 meter high, and the wind tunnel is basically 3 meters across by 2 meters, and they're both about 11 meters long, so they're relatively big. And this is kind of how we use the grids. So what's happening here is we're driving these with stepper motors, so we can prescribe a pattern to them. We're generally, in the way I'm going to show you we use them today, we're giving them random distributions of speed and rotation. And what you see is that basically as we go slower, we're getting a higher turbulence intensity. So these numbers that are on top, that's the ratio of the standard deviation of the velocity fluctuations to the mean velocity. So functionally, that's a measure of how intense the turbulence changes are in the flow, or the velocity changes are in the flow. So I've pulled off here particular numbers, but functionally, I don't know how many of you actually study turbulence in detail, but turbulence decays in space when you do generation in this way. So that's what this is a plot of. This is moving away from the grid versus essentially isotropic kinetic energy. And what you see as it goes down. So when I pull off explicit numbers there, it's really for one spot. But the point is that when I use this sequence, it's always more intense turbulence than when I use that sequence, for example. I can talk more about the nuances of driving these, but broadly what you want to know is that I can change the turbulence intensity and that this turbulence is roughly homogeneous, which means that if I measure it here or here or here, I'm getting the same numbers, same stats out. It also produces nice turbulence spectrum. So if you're familiar with what a turbulence spectrum looks like, it should look like this. So that's another benefit of using this, is that these are relatively high Reynolds number spectra. This is in dimensional space, so that's frequency versus power spectral density. This one is the laminar-ish one, which is why it looks different. And then as we increase turbulence intensity, it does this. And if we do dissipation normalization, we get a 5/3 law, which again, if you study turbulence, this is an expectation we have for what's called the inertial range. So basically, this is giving us a nicely behaved turbulence. You can do more creative things, for lack of a better term. So for instance, we can actuate the grid to make a sinusoidal pattern, so a sinusoidal gust. Here we can do impulse gusts. So if you look at this, this is time versus velocity, and these changes are about 30% of the mean velocity over a very short time. So it can be a very sudden impulse that we can drive it through. Or these are, this is spatial distance, and that's velocity, so we can create shear profiles. So what we've done here is we get the same shear for 4 different test cases, but this is turbulence intensity. We can increment the turbulence intensity. So kind of the broad thing you should be pulling away from these last few slides, what I'm trying to say is given the wind tunnel or water channel, we can dial in turbulence intensity, shear, intermittency, and then see how that affects another fluid mechanics problem. So that's what we're doing with these devices. And in that context, we're going to talk about 3 different ways that turbulence interacts with other fluid mechanics problems. The first is wingtip vortices. The next is waves. And the last one is gas transfer. So I'll talk about each of these when we get into them. These 2 are somewhat related to each other. That one is a little bit different, but some people here do aero, and this has some very nice visualizations and physics out of it. So I thought it was nice to show something that was more aero-based. This is more environmental and wave space. So why do we care about wingtip vortices? There's a whole bunch of reasons. Ultimately, at NTNU, where I come from in particular, there's a lot of UAV studies for doing surveying in the far north, for example, in terms of aviation, safety, landing distance for aircraft, and in wind turbines, assessing the impact of the next turbine down of the structures in the flow. So there's a reason to investigate wingtip vortices. What you're going to look at here is you can see this is our model. This is the airfoil. And the wind tunnel is starting at rest, and then we're turning it up. And you're going to see that the wingtip vortex starts to form here once we start to reach appropriate velocities. So there you can see it's starting to form. So this is the broad phenomenon we're looking at, is what's happening here. The reason you see some sort of coherent patterns in the background is because the wind tunnel started at rest. So that was just kind of the way that the seating was naturally carrying it around. This is an interesting phenomenon you see at a particular Reynolds number in our facility, that is literally the flow conditioning that you can see 7 meters downstream from the flow conditioning, because it's a very stable condition of the facility. But then it goes away, and now you'll see the tip vortex form nicely, and you can see the model. So what we're interested in is if I change the turbulence conditions in the flow, what does it do to this tip vortex? The main phenomenon we're going to look at is what's called meandering. So this again is just a visualization. We've got smoke coming off the wingtip. This is the wingtip vortex proceeding downstream, and then it starts to meander in the flow once a certain stability condition is reached. You can see here, this is the plane of the vortex, and you see it moving around. So we want to know if we have more turbulence interacting with this wing, what does it do to that vortex? This is just a traditional photography long exposure image. where this streak you see is the tip vortex moving. Because it's long exposure, we're just kind of seeing it as a blur. But what we're going to do is PIV so that we can see instantaneous images of what's happening. So the broad setup is we have our wing in the wind tunnel. We're doing PIV with 2 cameras. It's high speed. There you can see the setup as well with the cameras on the outside. This airfoil is a NACA 0012. It's 12.5 centimeters and the wingspan is 0.5 meter. And we've got an angle of attack of 9 because you need lift to get a wingtip vortex. The Reynolds number is about 100,000. Then we use our active grid to change the incoming conditions. And we get basically 4 test cases that I'm going to show you today, where our turbulence intensity is going from about 0, so this is as low as we can get it in the facility, 0.3, up to 13%. And then the integral scale, which is the rough size of the largest eddies in the flow, also scales with the turbulence intensity in this experiment. So they're not decoupled. And these are the turbulent Reynolds numbers, or RE lambda, that goes with these flows, if you're familiar with what these numbers are. But basically, the turbulence intensity increases as I go through cases that are called ABC. So the first question is, what does it do to meandering? Here you'll see 3 cases, and these dots are where the center of the tip vortex is. And you can see that broadly, it's being spread over a bigger and bigger area. The center of the tip vortex is we're increasing the turbulence intensity. And this is what the mean vorticity fields look like. So here, it looks like the vortex is getting bigger and bigger. This residue is just the wake of the wing. So these are the same plots, just plotted on axes. And what you would take away if you were just looking at this is that as you add free stream turbulence, the vortex basically gets bigger. But if we instead conditionally average, so in each picture, we take the center of the vortex and we say that's our 0, then we take an average of that. So we're recentering every image on where the vortex is. You actually see that's the same in every image. So as you increase the turbulence intensity, the vortex itself always looks the same. What's different is that its position is further and further apart. So that's why the time average looks like this. The vortex itself always looks the same, but because it's spread over a bigger area, you get a blurred out image, the average. So now we decompose this a little bit more. We do proper orthogonal decomposition. So for those not familiar with it, without going into too much detail, the way I think about this is if we understand the concept of, for instance, how a spectrum is composed, it's a series of sine waves where each sine wave has a different amount of power and you can put those back together and you get the signal. POD is a way of decomposing the spatial fields where you break it down into a series of different modes and then each one has an amount of power, and if you sum them all back together, you'll get back your original image. So these are spatial modes that contribute back towards the total field. And we break them down based on the ranked by energy. So this will be the most energetic spatial modes and then so on. There's actually 1,000 modes in this decomposition, but I'm only showing you the most energetic ones. Anyway, so when you look at these are kind of the spatial information that exists in our PIV images. This is based on vorticity. So these first 2 images, these are helical displacement modes. So it's basically the vortex moving in helical patterns. This is a further position downstream. So that was 12 chord lengths. This is 24 chord lengths. We start to see the development of this, which is a deformation mode. You go further downstream. We have these elliptical deformation modes that show up as well. So, and this starts to become repetitive after we get to a certain distance downstream. So this is 48 chord lengths and 36 chord lengths. This is all our reference case, so the case with no turbulence. This is basically the evolution of the spatial modes, what they look like. This is the energy part of this. So basically how much of the total energy is contained in each mode. And what you can see is that as you go downstream, so further away from the wing, these 4 modes that I'm showing you become more and more important. Now, all of this that I've said, some are helical, some are deformation modes. The real takeaway is that they look like this. And this is what we're going to compare these spatial modes to what happens when we add turbulence. We'll take this as a reference. Now here is the case when we add turbulence. So here, this was basically 0 turbulence. These are 1.8% turbulence. And you see that they look basically identical to each other. The difference here, though, is that that was at 36 chord lengths and that this is at 5 and 12. So basically what happens here is that when we add turbulence, we get the same spatial modes. So the flow is organized the same way, except it happens much, much closer to the airfoil. So the reason that it looks like it is spread over more distance and meandering more is because it's the same picture of the no turbulence case. It's just been pushed closer to the airfoil. And likely, I don't know the answer to this for sure, but likely this happens is because some instability is kicking in and causing the meandering. Then when you add turbulence, it pushes it. It activates that instability sooner. That's what we hypothesize is happening. Now, if you put a lot of turbulence, you start to then blur out these modes. You can see that ultimately they are quite similar to each other, but that this is now being spread over a bigger area. So if you put a lot of turbulence on, this is now 8 compared to 2, basically, then you start to really break down the flow. But here, we're seeing the same thing, and it's just been accelerated by the addition of turbulence. So remember there's 3 parts. So this is just what to remember from what we just talked about. We want to know, how does turbulence influence the propagation of wingtip vortices? In the mean, it looks like it's more dispersed. But when you take a conditional average about where the vortex is, you see that the vortex itself looks the same. And really the reason the mean looks different is because it is meandering more. And that the turbulence is promoting a more rapid transition to the final state, which is why it's meandering more closer to the airfoil. This was a submission to the Gallery of Fluid Motion, which is where I pulled some of those videos from. The rest of the talk is published. This is the only part that's under review still. So to learn more on it, you can see this video that we previously made if you want to know. So now we're going to move into the air-water interface part. And this is more based on the environmental concerns, the motivation of this part of the project. This is funded by the European Research Council. Both my colleague Simon Ellingson and I both have European Research Council projects based on how turbulence interacts with the gas-liquid interface. He's mostly interested in waves and turbulence, and I'm mostly interested in, for instance, how CO2 and O2 go across an air-water interface. I'm going to talk about both those things briefly. Whoops. And that's how we exit the talk. So here, what we're going to primarily look at is how non-breaking waves influence turbulence and how turbulence influences non-breaking waves. Some background for people that aren't super familiar with this space already is that if we have a wave, then we expect periodic stretching of the streamwise vorticity, where in the peak, you expect compression of the streamwise vorticity, and in the trough, you expect higher streamwise vorticity. So we're stretching out the vortices. And this should be a function of the steepness of this wave. Something else that we expect is that due to Stokes drift, which is basically orbital motions induced underneath the waves, or at least that's a consequence of the Stokes drift, we expect the vorticity to be translated into streamwise vorticity. So any vertical structure like this is going to be bent as it approaches the surface. So this is kind of the theoretical baseline in which we're looking. And we want to know, how does changing the amount of turbulence under the waves influence this? Does it always happen, or can you saturate the problem? And also, does this happen? Because there's some DNS that shows that it happens, but there aren't that many experimental measurements of that. So our facility for this is that we have our water channel with our active grid in it, where we can control the turbulence coming into the test section. We have a wave maker on this side. This is it operating as a piano key, so we can create all sorts of different wave formations, but ultimately in this experiment, we're just creating 2D waves that propagate upstream. And then what we're going to look at is how they interact with each other in the middle. Again, we're doing PIV, so we're going to get vector fields where we get the streamwise velocity, the spanwise velocities, and then the streamwise vorticity, so the vorticity in this plane. I'm going to interchangeably refer to that as the streamwise vorticity and the cross-plane entropy, which is the square of the vorticity, because a lot of the literature refers to this more in terms of the entropy context, which is basically the sum of the vorticity components squared. But really, entropy is a scalar that is the sum of all the components, and we only have one of them. So I prefer to call it vorticity, but now I'm in the diatribe. Anyway, what we want to see is how this vortical component changes as we change the turbulence flow. So first, we're going to look at what the waves does to the turbulence, or do to the turbulence. Again, this is the framework that we're expecting. So high vorticity under troughs, low vorticity under peaks. And broadly, when we do a conditional average, so basically we have several waves that go over, and we're taking this point every time and averaging it, and this point every time, and then we create this map, so on, and we get the right answer, basically. We have high vorticity in the trough, and low vorticity in the peaks. And this is mostly a sanity check. So this is telling us that it's doing what we expect it to do. So now we're going to get a bit more creative with the problem, which is we want to know do these effects last? So if I do that to the flow, does the flow remember that it had this stretching and compression? Or once the wave passes, is it just over? It's done. It forgets that happened. So the way we test this is we send a wave packet. So this is a wave that looks like this, and we send it upstream, and then we measure it 3 spots relative to the wave group. We measure way before the wave group arrives. So this is kind of the baseline in the water channel. We measure just as it arrives to see if anything has already changed in here. And then we measure it afterward to see what the wave did to the flow. When we do this, these are going to be our streamwise vorticity profiles. So this is normalized distance down from the surface, where 0 would be the surface, and it's normalized by the wavelength of the wave. And you see that in these first 2 regions, we have basically the same profiles. So this is what you'd expect. The turbulence here and here hasn't really changed. But now the question is what happens here? And what we see is that the streamwise vorticity has increased by 58%. So that's a quite substantial increase in the vorticity, and that has only happened because we passed waves over. So now the question is, if we put a different amount of turbulence in the water to begin with, does this still happen? And the answer is basically yes. So here we're changing the incoming turbulence intensity. And in every case, we're seeing between a 40 and 60% increase in the entropy. The one thing that's interesting here is this isn't really monotonic. So as we increase the turbulence intensity, we're not getting necessarily some similar pattern in how much entropy is increased. So we don't fully know the answer to why this is happening, but part of it might be linked to what I'll show you next, which is the effect of the largest eddies in the flow, which is a separate parameter from the turbulence intensity. So just before we get to that part, is this kind of an expected result? And the answer is yes, because we have 2 reasons to expect it. First, we have this phenomenological description where we're expecting the vorticity to be realigned in the streamwise direction. And second is this is the equation for entropy in the flow. So that's the entropy transport equation. And you have this term, which is production. So it's the creation of entropy. And normally you'd expect this term to be 0 because these gradients would be 0. But when you pass the waves over and you get this periodic stretching and compression, you're basically activating this term. So it's producing turbulence in that term as well, in addition to the expectation of the phenomenology of the bending of the voice. So we've verified that this happens and that it exists. Now the question is, what does turbulence do back to the waves? To do this is the same experiment. We're just now looking at it from above. The flow comes this way. Wave maker's here, it pushes waves up, and turbulence propagates this way. These are wave probes. And what we're going to look at is the phase shift across them. So what that means is, does this wave probe, what is the difference between this wave probe and this wave probe, for instance, Model 2? So if they measure the exact same thing, that means that there's a 2D wave going across it. But if they measure something that's different, it means there's a slight angle to the waves. This we map on as the wave angle. And then what you'd expect when you're very close to the wave maker is that this is a very sharp PDF, right? It's mostly 0-centered. But as the turbulence and the waves interact, the wave angle distribution diffuses. So this PDF becomes flatter and we get larger angles. Now the question is, how does this scale? You know, as you change turbulence, how does this change? Yep.
Do your waves have time to reflect off of the relative greater angle from the outside?
It's a good question. So this is done as ensembles. So we start the facility with running water, which does a lot to stabilize the surface. And then we send a group of waves up and we measure. And then as soon as the reflection starts happening, we stop the experiment. And then we do it again 100 times. It takes a long time. So these are the 2 most intense cases that we have. And what's interesting here is it's not the case with the most turbulence intensity that scatters the waves the most. It is actually the case with the largest integral scale. And again, for people not familiar with that terminology, the integral scale is the average size of the largest eddies in the flow. So what that's saying is that the size of the eddy contributes more to the scattering of the wave than how intense the fluctuations in the water are. So we haven't mapped this completely back to the other part of the study, but this might be the reason that we have a non-monotonic change with turbulence intensity, because the integral scale needs to be considered into that parameterization. So maybe if we had a singularized parameter that had turbulence intensity and integral scale in it, maybe we could create the entropy increase to be some increasing function or decreasing function in one way.
Have you looked at like what the integral scale is in relation to like the wave spectrum?
Yes, but I don't remember the answers. It's definitely in this paper though. I think we do talk about it in part of this paper.
Okay.
So in this part of the talk, we're interested in how do non-breaking waves influence turbulence. And the answer to that is that waves passing over turbulence increase the streamwise vorticity. And then how does turbulence influence non-breaking waves? Turbulence increases wave scattering, but this has a stronger dependence on the length scales in the flow than on the actual intensity of that turbulence. And this has that entire experiment described in much more detail in this paper. The last part of what I want to talk about is this gas transfer problem. I will motivate this with the ocean, but this has many industrial applications as well. Basically, the broad system that we're looking at is if you have some gas and some liquid that are separate from each other, you can have the transport of gaseous species across the two. So for instance, air is made up of many molecules, right? Water is also made up of many separate molecules. So there can be some amount of, for instance, aqueous O2 in the water that is transported there from the gas phase. For instance, that's what fish breathe. And that's also the largest carbon sequestration process on the planet is CO2 in the oceans. It stores about 50% of anthropogenic CO2. Now, the interesting thing in terms of the climate model perspective is that most models set that as a constant, that rate of transfer from atmosphere to ocean. But I will try to convince you that it is not a constant. And therefore, perhaps we should have some more information on it. It's also important in industrial settings, any mixing process where you have two phases. You have these gas transfer processes. And you can imagine this in the most simple system, right? You just have static air and static water, and then it's just a partial pressure problem. But as soon as you start to have flow, you have other physics that are also playing into the problem. So if you consider this most basic system, you have flowing air over liquid. This static, you're going to get some wave formation, and this K represents the gas transfer rate in this case. You're going to have some K that represents that. Now, if you start to add turbulence to the flow, that interface may look different, and this K may be a function of the turbulence as well. You can also have the case where the water is flowing and the air is quiescent. That'll put some interface topology, and it'll change the transport properties in the water. And then you can have what's likely the real case in most systems, where everything is turbulent, everything is flowing. And right now, we can't really predict what this number is. Again, I will show some examples from field studies in the ocean because there's a good database for this. This is one application of this knowledge, but the ocean is not the be-all, end-all of this problem. What you're looking at here is reference wind velocity at sea. So this is 10 meters above the water. This is what they usually use as a reference, if you're not familiar with this. And this is the gas transfer velocity normalized to the Schmidt number of CO2. And what you're looking at here is several measurements from many campaigns, and you can see there's some general trend where this number, so the gas transfer rate goes with U10. But what's interesting here is if you look at the range on here, this is like 100% scatter in these plots. Now, the reason there's so much scatter is not because these measurements are bad, it's because it's really hard to control this. There's all sorts of salinity and chemistry problems out there. The conditions are not necessarily stable. The sea state is changing. So these are very good measurements. It's just that there's a lot of parameters here that aren't in the control of the measurement. So what we can do in the lab is try to control those conditions better.
Yeah, so just to be clear, all of these four scenarios have this in the data, right?
Yeah, so this is like this. That's except they can't, they can only measure that, but what they've got in the out there is this.
Okay.
And there's a whole bunch of models that do a relatively good job of predicting things in this environment. But this is kind of the space that you're working in if you're outside. So what we want to know is, can we kind of figure out how much of this is due to physics of turbulence? And can we then add to either a description of what's going on here or even prediction if we know certain turbulent characteristics of the flow? And what I'll show you is the first experiments we've done in this area that are focused on that one, the sea condition. So the way we do this is in our water channel. We have our active grid to change the turbulence. We have a mean flow. And the first thing we have to do is get the oxygen out of the water. Because we're going to look at oxygen transport because the lab is much happier to let me put lots of oxygen into the lab rather than CO2. Then the way we do this is by using sodium sulfate, which bonds with the free O2 in the water to create sodium sulfite. And so there's no free O2 in this. So I'm not talking about breaking H2O apart. I'm talking about the O2 that's already in the water. I'm bonding it to something else so that when I put a probe in to measure how much O2 is there in the water, the answer is 0. And that's free O2 in the water. Then what we do is we allow oxygen to re-enter the water from the lab because there's abundant amount of oxygen just in the lab. Then we have to measure this in some way. So we put an oxygen probe, which will give us the bulk oxygen concentration in the facility. We use a laser and we do PIV to get what the flow is doing. We do laser Doppler anemometry or velocimetry to get higher temporal resolution of the flow. Then the surface might deform as we have turbulence. So we have wave probe just to get statistics of the surface. And we used a few different high-speed imaging techniques, including synthetic Schlieren, to get what the surface is actually doing so that we can kind of decompose what's happening in this problem. One key difference between this experiment and, for instance, the ocean is that this is basically a continuously stirred reactor. So that means that this flow that goes out goes around in a loop and then comes back in the other side. So in the ocean, that doesn't happen. There's a giant sink, but in the lab, that's what's going on. So every bit of oxygen that goes in here will then go around in the loop and then come back. So we'll keep building up the oxygen in the test. But we do all of this to get curves like this. So what you're looking at is this is time, and this is dissolved oxygen concentration. It's in percentage in this plot, so it goes from 0 to 100. So this means there was no oxygen in the water, free oxygen. And that means that we get back to the saturation amount, so how much the water can take. One thing you might notice about this is that this goes up to 50 hours. So this experiment took 2 days to do of the thing continuously running. That's measuring the oxygen. And your main takeaway from this is that these curves go like this as turbulence increases. This may not look that different from each other, but if you look at the gas transfer rates that are calculated off of these curves, you'll see that this is actually a 30% increase. So imagine you've got some industrial process and you're trying to calculate how much transfer you're going to have, or you're calculating the total ability of the atmosphere to transmit oxygen into the oceans. And your number can vary by 30% based on those flow conditions. And in both cases, you're not considering what the flow is doing in the water phase. So that's kind of the impact of this, is that we can show that based on the water turbulence alone, the gas transfer rate changes by 30%. So the first question that we get often from people is this because the surface changed? We added more turbulence, so then the surface started to move more. And the surface did start to move more. What you're looking at here is our synthetic Schlieren. So this is a 16 by 16 centimeter area. And what you're seeing the surface do is amplified by an order of magnitude. So this is only plus minus 8 millimeters. And as we increase the turbulence intensity, which is those numbers, we are seeing the surface move more, but the total surface area increase is 0.2% for this compared to this. Remember that this axis is amplified by an order of magnitude, right? So it doesn't actually look like that. So we, in this first work on this, we said it probably isn't this that's driving the 30% change in gas transfer rate. But we wanted to know more about this. So we created this next experiment on the topic, which is we still have our active grid, we still have our water channel, but now we're deliberately making waves with these dowels. So these dowels they're literally little needles. When you look at this, you don't want to fall into it. It looks like an Iron Maiden, or like one of those things you would try to walk across. And the reason we do this is twofold. One, some experiments have done this before. So there's a basis that people have used this mechanism to create waves. And two, you get this very nice bow wave formation. And actually, there's an analytical solution for this. So if we measure at 1 point, we can get the entire surface area based on the analytical solution. So that means I can tell you exactly what the surface is doing everywhere. So that's a motivation for the setup as well, that we know what the surface is doing. So then what we're going to do is basically the same experiment, but now we're adding waves, turning them on and off on purpose, instead of them just being a function of what the flow is doing. In this case, we're using a surface lift technique where basically we put fluorescein, not fluorescein in this case, this is rhodamine in the water and nothing in the air. So then we can basically just shoot a laser at it, and wherever it's fluorescing is water and wherever it isn't is air. So we can draw a nice clean line across the air-water interface. And that's how we get the statistics for the interface in this case. So this is a giant table. I don't love showing giant tables, but I'm going to show it to you to step through the test cases we look at. The first one is just the test name. That won't be that important. The next one is whether the grid is on or off. The next one is the dowel configuration. So that is how we've actually used those needles to change the surface. This next column is turbulence intensity before it reaches the dowel array, integral length scale, so signs of largest eddies before it reaches the dowel array. Then this is the surface fluctuations, so literally the standard deviation of the change in the surface. And these are the mean squared surface slope. So mean squared free surface slope, which is basically a measure that's been used in several studies to characterize how deformed the surface is. The first one comes off of our measurement, and the second one comes off of that analytical model I said, where we can get an exact result for the surface. Then the next one is a bulk turbulence intensity, which I'll show you in a second where we calculate that. And the last one is the answer. So if you want to know what happens, just look at the last column before I show it to you. But anyway, our first case, well, let's go back. Our first case is just the water flowing. The surface is relatively flat. If you look at our metrics, we have this turbulence intensity, and these numbers are relatively close to zero. Then our next case, we put the dowels in. So our turbulence intensity hasn't changed so much for the first two cases, but you can see that our mean squared surface slope has changed by an order of magnitude. So basically the surface is much weightier. Then our next case, we put the dowels deep into the water. And the reason we do this is we've seen some other studies had done this, put them deep in. And the thing is, these are basically cylinders and they start to shed vortices. So you get some turbulence. And you can see there's a turbulence jump here between these two cases. Then what we want to do is create one number that represents the turbulence in the whole profile. So we take the turbulence intensity profile and we integrate it to get one number. When we call this the bulk turbulence, this is equivalent to the bulk velocity. So if you're familiar with the closed flows, the bulk velocity is basically a velocity scale that's the mass flow rate. So this is a turbulence scale that's equivalent to that. It's an integrated number for the whole flow profile. So now this is where things get interesting. This is kind of what people had done before. We use our active grid to, as close as we can, make the same turbulence intensity, but now there's no waves on it. So what we've done is we replicated this test case by removing the waves, putting the same amount of turbulence into the flow. You can see that the surface is very different. So for instance, when we had the dowels deep, the surface slope was 15, now it's 1. So this is more close to when we had nothing going on the surface than it is to when the dowels were in the water. And then the last case, we just put everything going. So we have the turbulence in the water, and we put the dowels touching the surface to have both the waves and the turbulence. And the idea here is basically that we've tried to decouple the turbulence in the flow from the dowels. So the dowels turn the waves on and off, and the turbulence in the flow is a function of the active grid or of putting the dowels too deep into the water. So in all those test cases, we do these measurements again. So this time we've just normalized it such that it goes from 0 to 1. Again, this is saturation, that means no oxygen. This is time, and now we're going up to 80 hours. So my PhD students were really pleased to do this experiment for so many days. They did go home in between because it just ran overnight. But so this is a really long experiment. And we see that turbulence intensity goes like this, and the ultimate consequence is down here. So this is the mean squared surface, and this is the gas transfer. And what you see is that there's no clear correlation here. But if you plot it versus bulk turbulence intensity, there's a linear relationship. So basically, what it's telling us is that in this system, the flow and the gas transfer rate cares a lot about what the turbulence intensity is and doesn't care so much about what the surface is doing. And this time, it was a 45% increase in the turbulence. So again, this number is treated by a constant in many modeling applications, whether they're industrial or environmental. And by just changing the flow, we're able to change things by 45%. We bring this back over to this map, and we say, what is the consequence of all of this? So if you try to take this in, what it means is that for variations on these scales, we can now attribute it to some degree to flow physics. So we're not there yet, but it means that perhaps we can make predictive calls about how much variation you should expect if we knew more about what the fluid was doing, instead of having these relatively scattered distributions. But again, here, that's an environmental one, so there's a lot of things not in control when you're measuring that. And by no means should anyone understand that I'm saying this is a bad measurement. It's just a very difficult measurement. So the things you should remember from this part of the talk is turbulence more important than capillary waves for gas transfer? Ultimately, the answer appears to be yes. The gas transfer scales linearly with the turbulence intensity, and there's no clear correlation with what the waves are doing. However, and this is important, usually when I give this talk, I put it out at the front too. It's really important to not apply this result to anything other than the cases in which I just showed it to you, in the context of we made non-breaking capillary waves. So that's like what you might see coming off of a duct, and it's like that pattern I showed you. These waves, there's no breaking, there's no gas transport, there's no bubbles. So when you start adding all of that, then this conclusion doesn't necessarily hold because there's other processes that govern that process, but the gas transfer process. But here, whenever the waves are just capillary waves, the turbulence seems to play a larger role than the capillary waves do. And this is detailed in these two studies. This one was just accepted and the other one's already available. So the last thing I just wanted to show you and talk about is all of that gas transfer studies were done with bulk measurements. So we put a probe in and we're basically measuring the integrated amount of O2 in the water. But what we want to know is how is the turbulence actually responsible for those changes? So what you're looking at here is image of particle image velocimetry, that's what the vectors are, combined with a laser-induced fluorescence technique that is actually illuminating oxygen. So what you see here is calibrated to oxygen content. And you see that there's the most oxygen near the surface, and then you will occasionally see a structure go through where the fluid is training down a big chunk of, for instance, high oxygen concentration. And the whole point of this measurement is to give us access to understanding why that is the result. Not just you add kinetic energy and you get more gas transfer, but what structures are actually responsible for pulling down the high oxygen concentrations, and we can calculate the fluxes from this too. So the way we do this is we combine three existing techniques. So the first thing we do is this surface lift technique. So there's rhodamine in the water, like I said before, and there's none in the air. So then we can binarize this field and we can get a nice interface of where the air-water interface is. This is a technique from Buckley and Veron and other people that have used it before, so we didn't make this technique. You can combine this with PIV. So you take this and you apply it as a mask, and this lets us get vectors very close to the surface, so we can have a good understanding what the fluid is doing. Again, PIV is not new either. And then we combine this with an oxygen lift technique, which we first read about in this paper, which they cite even earlier papers that were using it for bio applications, for example, where we put an acid, BPA in, and it's basically quenched by oxygen. So that means that the dark spots are where there's oxygen, and you can calibrate this such that you can get actual concentrations in your field. So what we did is we basically combined these things together to create a system where we can do it all at the same time. And that's how you get fields that look like this. So this is the video that's playing, and these are 3 instantaneous snapshots. And what you see is that we get the velocity field, and we can also get the concentration of the oxygen instantaneously, and we see how they're correlated to each other. And broadly, the most common thing we see are these sort of structures where you get some vortical elements, and it's peeling off some high concentration down into the flow. And so previous DNS has said that it's these sort of instantaneous high intensity events that are responsible for predominantly for gas transfer statistically.
So this seems highly effective. So is there a Peclet number that you can define?
So we don't have, I don't know about the Peclet number, but the nice thing about this is that usually when you're doing this in, for instance, DNS, they're limited in what the Schmidt number they can do is. They usually use a Schmidt number of about 1.
I see.
But this is actually oxygen that we're looking at. So it's the correct Schmidt number for the problem because we're looking at the real thing. And the Schmidt number of this is about 580. And for CO2, it's about 660. So in terms of once the two gases get into the water, they behave similar to each other. I should look at the Peclet number. I don't know what the answer is. Yes, and then another like just sanity check thing is what you see here is that if you look at different times that the background intensity increases, which it should because more oxygen is getting into the system. This is in a much smaller rig, which is why it only takes about 2 hours for it to get to saturation. The big water channel is 40 tons of water. This facility is about 70 liters. So the last thing is just to talk about our new facility. What we've got here is a standard water channel where the flow goes around like this, but we've got our active grid and we've designed a splitter plate that is deliberately set up so that it kills the surface deformations. So this water is flowing, but it looks like it's close to not flowing. And the reason is that we don't want the active grid to directly impinge on the surface. So anything that happens on that surface, we know is a vortex that's in the flow and then comes up and interacts with the surface. Then what we would do is we have airflow over it, also with an active grid in it. So this airflow can go up to 10 meters per second. This doesn't necessarily mean we can do like huge waves outside, but it does let us change the turbulence on both sides of the interface. And we have independent control of these two active grids, which means we can dial in things like turbulence intensity and intermittency separately in the water and the airface, and then see how that impacts the interface and how it impacts gas transfer. which means that we can access this entire matrix of problems as opposed to just accessing one of them. So we can get to here, basically. And these are just two videos showing you the flow as we propagate downstream. One way we can simulate worse sea conditions is we also have a wave maker in the facility. So that's the difference between these two videos. That is just wind-generated waves. This is with wave makers. So I spoke for a bit. If you remember anything of what I said, it's that you should remember these 3 points. So wingtip vortices mature more rapidly when there's turbulence, which means that the vortex itself stays the same, but its instability is activated earlier, so it moves around more closer to the wing. Waves increase subsurface streamwise vorticity, and turbulence increases wave scattering. And the last thing is that in terms of gas transfer at the interface, subsurface turbulence plays a bigger role than the interface itself does, and as long as you stay in the non-breaking capillary wave regime. Almost everything I showed you is published, and this is where you can see it, except for the wingtip vortex stuff, which has a fun video and is under review right now. So thank you. If you have any more questions, feel free to ask them. This is our like black hole wingtip vortex.
Any questions?
So this already seems like a very big device to me, but I'm sure that the bounding walls are still influencing the vortices because you cannot have one that's bigger than the system. But in the oceans, you can have them. So is there anything you see in your device that cannot be transferred to these larger scale problems?
Yeah, so I think sometimes I struggle with the afterthought of the conversion to the ocean, because really this is bound by its boundary conditions,
Yeah.
right? So I think what we've shown is that the turbulence intensity matters more than the surface waves to the gas transfer in this process. Now, how much that relates to, for example, large laminar circulation versus impulse turbulence under the water and the sea, I think is a different question.
Yeah.
So I think we've just looked at the physics of a very specific problem that has applications out there. But indeed, if there was some giant, like bigger cycle going on, we can't capture it. And I don't know the answer.
Is there any theoretical technique or potential theoretical technique to map the small scale to the larger scale?
I don't know the answer to that one. Do you know what?
No, because it's a highly you go out in the ocean, you're looking at a patch of the ocean, and it's a transient phenomena. So usually what you can do is, you have a patch of the ocean, and then you're saying that on average, this is what's happening. But in reality, what matters is the transient events are really contributing a lot to the dynamic. So it's not really something that you can just kind of model. So like you can do a lot of these, what we really do with the smaller scale experiments is we're looking at the transient physics, and then that'll hopefully inform better models for the larger scales.
So to what Martin's saying, I think it's this is something we hope to find with this, is that I showed you those mean curves changing, right? But there's a lot of evidence that suggests like these events that I pulled out, that these are the reason it's changing, and this is transient, right? Instantaneously, most of these images look like this, right? It's just a constant gradient. But every now and then you have one of these events, and that this makes a huge difference to the total statistics. So identifying how often this happens or what its value of contribution is might have some meaning. But we're trying to basically understand the base physics to then maybe allow other people to incorporate it into a bigger model.
Did you experience any problem or influence from wave resonance frequency basically, and may influence any of the measurement? And I first think about this when you have the increase and decrease for the second study, the wave study.
Yeah, these wave groups, right? There they are, these.
Yeah.
Did we have problems? Very likely. The postdoc that did this tested many different things. And the reason we ended up doing ensembles, like kind of related to your question, is that there's a big sloshing mode that happens in our facility. And there certainly were reflection problems if we ran the test for too long. So I don't know for sure about resonance, but the way we did all these experiments, is we did a lot of tuning to make sure our wave group was doing what we expected, and we'd send one wave group. This entire experiment would be done in 10 seconds. Then we'd wait like 20 minutes, and then we'd do another experiment to try to avoid any contamination of things we didn't want. I don't know specifically about the design of this wave packet. Probably there's more details in the paper. But I forget basically we tried to make sure there were no problems like that. But I forget how we went about making sure there were no problems. Other than that, this was all done in ensembles.
Go ahead.
I'm intrigued by this. Earlier in the first part of the talk, you had this ramping up of Reynolds number and showing
The video.
the video, yeah. Can you explain what's going on with that honeycomb formation?
Yeah. So this is like a classic thing that you discover something that's kind of cool, but then like you need a human being to actually investigate it further, right? But all the human beings that work with us have already like projects that they're on. But so what we think is happening, I'll try to pause the video at like the key point. Is that so in this whole video, we're increasing the velocity, right? So it started from rest. So we wouldn't actually like do this experiment this way. It's just a nice visualization. So there, I'll pause it. So what we think is happening is that you get to a certain Reynolds number where basically the flow is not mixing as it comes through the honeycomb. Because what's interesting is this is the honeycomb shape, right? The honeycomb is 7 meters upstream of where this plane is. And there's 2 mesh screens downstream of the honeycomb. And you can see it. And the reason that for a while, we're like, we must be seeing the honeycomb. Is the light reflecting off of it? Like what's going on? But you can see that it's being deformed by the vortex. And like, this is not an optical, like there's no density gradient here. This is not optics. This is the smoke is in this shape for some reason. And then when we look at the PIV, we can see this in the PIV too. So we avoid this Reynolds number for tests because this is not actually desirable. But it's like whatever mixing stability thing happens normally, we just hit some condition where it doesn't mix. And then this has just been transported for 7 meters as it is until it hits the vortex, which then mixes it. So we are kind of interested in just doing PIV on just that. And when I showed it to a colleague, they said that someone else had showed something like this, like you pass flow through a tube and it just remains like that forever. But it also says that our flows must be pretty laminar otherwise. So I guess if we want to do a laminar test, we should do it at this velocity. But that's what we think is going on here. And the reason we have some confidence that this is the flow is primarily that shape is deflected by the vortex. That is definitely not a density gradient. So you can see it there. That like it's clearly being manipulated by the flow. And that it's really far away. Like your eyes can't see that. When you're standing there in the wind tunnel, you don't see the honeycomb with your eyes.
Is your smoke injected downstream of the honeycomb?
So this video I mostly show because it's nice to look at, right? Functionally, the way the wind tunnel is it's recirculating. Our main smoke injection is downstream of the test section, and then it gets entrained into the fan, and goes around the loop, and then comes back into the test section. That's also why in this video it seems intermittent where the smoke is, because it's literally at the start. We see the test section, and then we're starting to film the whole time. Usually when we're doing PIV, it looks more like the end of the video. It's more like this, because we're just constantly putting a little bit of smoke in there, and it's pretty uniform through the whole loop. So in terms of our seeding, we're quite confident that it's good usually. It's just this video is really aesthetically pleasing to look at, and it clearly shows the phenomenon of the wingtip vortex in it. But I do think it's interesting. I'd love to investigate this more and see if we could diagnose why that happens. It's interesting.
I have a quick question. So I'm not familiar with gas transfer. Is the gas transfer velocity dependent on how much gas is already dissolved in the liquid, or is it independent of that?
So one thing that's in the recently accepted paper that's on that measurement technique, we show that the gas transfer rate in the profile changes as you increase the amount of gas in the liquid. So it's actually interesting because I'd say the consequence of that, so like we can measure the fluxes, right? The flux changes in time. So what that means is that people that have done similar measurements at one time is a transient phenomenon. So where are you in this spectrum of basically, I wish I had the figures in this talk, which I don't because it's really fresh. But let's go to any of these gas transfer curves there. So basically, if you did those flux measurements, like those images I was showing you here versus here versus here, you get different answers. Which I think actually is there's a consequence to that. Because we've looked at these measurements before, where were we on this curve?
Yeah.
And when you're in the sea, where are you on this curve? Because you get a different answer.
And you said that the turbulence in the water influences the amount of oxygen. But could it be that the turbulence is changing the wave energy like the surface wave spectra that's causing recirculation in the air that's then dissolving more? Because it feels like it should really be something that's air, like controlled by the air and not necessarily by the water side.
So two things. One, this is the surface spectrum. So basically, these are cases without turbulence, and these are cases with turbulence. It's not so great because it's based on lift, but it's still there. Just because you said it, so that's what it looks like. So generally, these gas transfer processes are, for at least CO2 and O2, are understood to be water limited, because basically the Schmidt number in air, so the relative diffusivity is so high that if there's suddenly a spot where there's low concentration, and relative to the timescales of what's going on in water and transfer, it just gets filled again. That is something we are going to investigate in the project. Like we will change the turbulence to see if that changes from just the air, or basically keep the water the same and see if it changes anything.
Yeah.
But like the reviewer said, and much of my reading says that basically the air shouldn't matter too much to the problem, other than what it does to the surface.
Okay.
But we'll see.
Any last quick questions?
Quick one about that, lift surface measurement with the road, I mean.
Yep.
So you're looking through the window of your tunnel, you have your laser plane somewhere, how 3D can it be before you can't really actually resolve the interface where your laser plane is?
Yeah, we're having fun with that right now in the experiments that we're doing. So generally when we're looking at it, we tend to look at it from above, such that we can always see the line. So not directly above, but from like, 15, 20 degrees, and we calibrate that out, that we're looking at an angle. That makes sense. Where we're having fun right now is we're doing transverse measurements, and the laser's coming in from the side, so there are some spots where you just end up in the shadow of the laser.
Yeah.
So where we're getting good wave measurements are from, we're doing air and water simultaneously. And the water one, we can get the surface out, but not from the air side because of this shadowing problem. Yeah. Oh, you said something in your question, maybe you wanna answer another question that was out there. Oh, well. But it's broadly is a pretty good technique and it's pretty robust. Any other questions? And it's pretty simple if you're doing PIV, because rhodamine just fluoresces with the same laser you do PIV with, and you just need to put some bandpass filters on your cameras to separate them from each other.
Okay, well, let's thank our speaker once again.
Thank you for the questions, discussion. Unplugged.